Good morning, everyone. I hope everyone's day is going well. My name is Aditya. I'm from Indian School Baucher, and I'm going to be giving you a slide overview of organic reactions. So now, this presentation will explore the key organic reactions involved in the conversion of the following reactions: ethene to ethanol, ethanol to ethene, and ethanol to ethoxyethane. Now, let's have a look at the structures of ethene, ethanol, and ethoxyethane. This is structure of ethene. There is one carbon and another carbon, and they are linked with a double bond. One hydrogen here, one hydrogen here, another hydrogen here, and another hydrogen here. So now the four bonds are there with each carbon, which is satisfying all of the valencies. Next, we have the details about the structure. The bond length of the CC bond is 1.34 angstrom, which is this bond. CH bond is 1.09 angstrom, which is this bond. Now, these are the bond angles as well. Now, let's look at the next structure, ethanol. This has two carbons, but then this time they're linked with a single bond. One OH, which is the alcohol functional group. Hydrogens to satisfy valency on both sides. So this is how ethanol looks like. And the bond length of CC is 1.54 angstrom. And you may be wondering, why is this bond length more than this one of ethene? Now let's find a slight trick to understand this better. Assume both the bonds to have an equal volume. You can see that this bottle is taller and is thinner, while this bottle is slightly shorter in comparison and it's fatter. If we take thin in correlation with single bond and thicker with double bond, we get a relation that says the thinner bottle or single bond will be taller and will have a larger bond length. So this is a nice trick to remember in exams when you are not able to get the concept behind it and all you see is a bottle and your pen. Now let's see ethoxyethane. This is also again quite an easy structure to remember because it is symmetric. This consists of two ethane molecules connected by an oxygen. This is the ethoxyethane molecule. Carbon, hydrogen, oxygen. No double bonds here. And these are the details: 1.53 angstrom bond length, 1.09 carbon hydrogen bond length. Now let's look at the actual reactions. Ethene to ethanol. The gist of this is protonation of alkene to form carbocation by electrophilic attack of H3O+, nucleophilic attack of water on carbocation, and deprotonation to form an alcohol. This is the mechanism behind it. There is a hydrogen ion formed. This ethane molecule attacks the H, which then makes it a carbocation and water separately again. The carbocation on the C plus attacks the oxygen, the lone pair on it, and then it makes this compound, and then H2O is attacking the molecule again to make ethanol and the hydronium atom again. This hydronium atom is the same one as used here. So this means that this reaction will keep undergoing continuously again and again. Easy trick to remember this one is you take an ethene molecule, CH3, add water, add in an acidic medium, and then you get ethanol. If you are wondering how this happens, I'm sorry, it is ethene here. Yeah. So CH2, water, H plus, OH minus. We are separating it like this for the ease of understanding. One goes here, one goes here, and then we get our ethanol molecule. The factors: temperature, pressure and catalyst. Temperature affects the reaction because when you increase the temperature, the reaction moves forward with high speed. Higher pressure can drive the equilibrium towards the ethanol product as per the Le Chatelier principle, which we have learned in grade 11. Catalyst: strong acid catalyst such as sulfuric acid can significantly increase the rate of the reaction. Now let's look at ethanol to ethene. The gist of it is protonation of ethanol, formation of carbocation and elimination of a proton. Here's the mechanism for it. The ethanol molecules attacks an H plus, and then we get this compound protonated ethanol, and then a bond is broken here so that the H2O is removed, and so a carbocation is formed, and then this bond collapses into the molecule, making a double bond here, and then this H plus is liberated, which is again used here for the continuous growth of the reaction. Factors, the same thing: temperature, pressure and catalyst. Now a way to remember this is ethanol, CH3CH2OH in presence of concentrated H2SO4 sulfuric acid. This is a dehydrating reagent, and this will immediately remove a water molecule. For example, you can see this CH3CH2OH. For ease of understanding, I'm going to draw an extra H over here. This OH as well as this H is eliminated, and what we are left with is ethene, CH2 double bond CH2. So I hope this makes it significantly easier to understand. The next one, what we're looking at, is ethanol to ethoxyethane. Again, breaking it into small parts: protonation of ethanol, nucleophilic attack, and deprotonation to form ethoxyethane. We have the same factors here. The mechanism is there's an attack of the ethanol molecule on H plus in presence of H2SO4 at 413 Kelvin, and then this intermediate is formed in which the bond between the C and O is broken to liberate an H2O molecule, and then we get CH3CH2 plus, which is the carbocation. This carbocation again attacks the lone pair on the oxygen of the ethanol attacks the carbocation, and then there is a rearrangement to get ethoxyethane. An easy way to understand this is drawing two ethanols, CH3CH2OH plus OH CH2CH3. Now as you can see here, we need ethoxyethane. What we can simply do, remove this water molecule. What we get as a result is CH3, CH2O, CH2, CH3 plus water. I hope this makes it easier to remember in exams. Factors as usual are the same. Now, any questions from your side? Yeah.
So you will explain about the mechanisms, and all the mechanisms had a step called protonation. Can you explain what protonation is?
Protonation, yes, I can explain that. Wait, your question is to explain what is protonation, right?
Yeah, what is protonation?
Yeah. Let's take one reaction for example. Let's take this one. Now here, protonation means this H plus is being attacked on by the lone pair of hydrogen. So when this attacks this gives the OH an opportunity to become a water molecule and break off. So this H plus molecule, which is a proton, because it has a plus charge, and as we know hydrogen only has one electron, this plus charged hydrogen is basically a proton. So when this proton is added to the reaction, it basically acts as a starting point of the reaction to help accelerate the growth of the reaction and carry it forward. Any other questions? Yeah.
So ethanol to ethoxyethane follows SN1 or SN2 mechanism?
Okay, that's a very good question. As you might have studied in the the sixth chapter, SN1 reaction, the reactivity series is 3 degree comes first, 2 degree comes second, and then 1 degree comes last. This is the reactivity of SN1. SN2, it is a completely opposite reactivity, 1 degree, 2 degree, 3 degree. In this reaction, this is a 1 degree alcohol because there is only one carbon attached to this one. So if we see, then SN1 would be extremely difficult for this to progress under normal conditions. So this is an SN2 reaction. Your question please?
So you said ethanol to ethoxyethane, the mechanism you showed. Can that be used for preparing asymmetric carbon compounds?
Asymmetric carbon compounds. I don't see why not. If we have two different alcohols in the same mixture and we take this reaction forward, we would get 3 ethers. 2 of them would be, both of them, the 2 ethers combined by themselves, and 1 of them will be the mixture. Let's look at an example for this as well. What 2 alcohols do you want to take?
Let's take ethanol and propanol.
Ethanol and propanol, fine. So first off we have ethanol, CH3, CH2OH, which gives us ethoxyethane, CH3, CH2O, CH2, CH3. This is fine. And also let's take the propanol as well. So this is the ether we would get when we are doing the reaction with only propanol. Now let's take both of them combined. We get CH3, CH2OH as one molecule, and the other one as CH2, CH2, CH3. This is our alcohols, and again using the trick which I had shown earlier, we just remove this water molecule from the combination of them, and then we get CH2, CH3, O, CH2, CH2, CH3. So yes, this method can also be used for preparing unsymmetrical ethers. Beautiful question, thank you so much.